is a close friend and collaborator. She's a pioneering worker in the area of quantum science, particularly optics. Some of you who might have seen her work, they are actually, to start with, very oriented towards very fundamental aspects about superposition, Born's rule, and truly, very fundamental, basic aspects about light and its nature. And she has continued pursuing that. On the road, you can see that technologies are beginning to come out. She's actively involved with our ISRO in a project in the same name, QUEST, which is aimed towards quantum communication through space. And now she is an active participant in this present QUEST project, which is ongoing. And quantum communication, entanglement, its characterization, and many basic aspects of light she has been investigating in her lab, this LAMP, in Raman Institute. And if you are, she also sort of loves to popularize it. You might have seen her Scientific American article. Some of her New Journal of Physics articles are very well explained, many basic aspects, very transparent way. So all along you see, not only understanding the basic nature of night and interference and other kind of phenomena, but also using it for technology has been the landmark towards which she is aiming at. I have been fortunate to be a member of this Indo-Italian project, where some three theorists, Professor Dipankar Rom, Guru Prasad Kaur, and myself, we are associated with her. And the experiments are going on in RRI. Hopefully, light-based, silicon-based, chip would be a product of that. Let us hope for the best. But as you know, it is a challenging task to come out with quantum technology. The ecosystem has to be built in. So there have been effort from the government side, and multiple agencies, multiple institutions are involved. And one of the key institutes is Professor Urbasi Sinha's group in RRI and others also. So now I request Professor Sinha to give a talk, 50 plus 10 minutes, and questions will be there. So Professor Sinha.
So thank you very much once again, Professor Panigrahi, Professor Pal, and all the organizers of QIQT 2022. So first of all, I'm really very honored for this extremely warm and kind introduction, Prashant. It's a privilege. I'm very lucky that I was also, one of the speakers in the in-person QIQT that was held. And of course, you have maintained the tradition, had it online and now in hybrid mode. And I think it's always nice to, come back and say something in your conference. It's very well organized. So thank you very much for this opportunity once again. I will share my screen now and then hope for the best. Can you see my first slide, Prashant? Yeah, you can see it, right?
Yeah,
great. Yeah, so thanks a lot. And so with that, it's also an honor to actually begin the workshop this time. And I hope I provide a little bit of a good start to it. And of course, I look forward to the rest of the talks and events during this 4-day period, as well as the extended period. So what I decided to talk to you about today is on revealing new facets in experimental quantum information processing with photons. Given the time frame, the time allotted for the talk, what I would do is talk in detail about one of our very recent experiments on the Leggett Garg inequality, and then give you a little flavor of some of the other experiments that have happened in recent times without going into a lot of detail with those. This is the website for our lab, so please have a look for more details on various things that may interest you as we go along. And of course, the lab is incomplete without its people, and so we are very lucky that different sorts of people have chosen to join us in postdoctoral, PhD, as well as engineering capacities. As Prashant mentioned, for the project with ISRO, we do need engineering support and for other projects. So we are very lucky to have this very nice mix of different people from different backgrounds. This is a snapshot of different experiments in the lab. As Prashant already said, one of our key areas is, of course, our explorations in the fundamental tests of quantum mechanics, which is on superposition principle, Born rule, and several others. And in fact, this is a very area in which we have been doing quite a bit of work and experiments as well as theory. Here you have some of our work on quantum optics and quantum information, and the ones in red are highlighted because, they will form a part of this talk. Okay. Entanglement studies, entanglement measures, both static and dynamic properties of entanglement. In fact, we are very nearing, the completion of an experiment on manipulation of sudden death of entanglement. And in fact, a couple of PhD students of Prashant were involved for some time in this experiment here at RRI as well. We are working on generalized measurements and weak measurements as a tool, and have done, and I would love to talk about this perhaps, in the next QIQT, because this time I decided to focus on some other work that has happened in recent times. For instance, these two, which will feature during my talk, which is on our approach to higher dimensional quantum information processing involving both computing, communications, as well as fundamental studies in the same. As Prashant very nicely summarized, our lab's endeavor is to actually work on fundamental aspects of the problem while applying these to technological ramifications as well. And in the process, we have had both publications and patents from the lab. And so this is something we would like to continue. In the quantum communications domain, we are working on experiment, again, short form is QUEST, but this is quantum experiments using satellite technology, which is India's first project in this. And we have done several ground-based milestones in this regard. We are working on this integrated photonics QKD, where Prashant is also a co-PI along with others, and it's going very well. The free space experiment is happening very well, and we hope that it will lead to some very nice results in the near future. We're working on the DST Quest umbrella. We are working on quantum teleportation, repeaters, and relay technologies, which is again a long distance communication approach. And we have the Center for Excellence from MIT, where I am the PI from RRI along with co-PIs. Our lab is specifically working on device-independent random number generation. And in fact, the experiment which I will talk to you about in some detail today is being used for that purpose as we speak. So plan for the talk is to spend more time on this first result, which is on the first experimental loophole-free violation of the Leggett Garg Inequalities. Then go on to some detail about the direct determination of different entanglement monotones used to quantify entanglement in arbitrary system dimensions using only one pair of complementary observables, as well as an experimental proof of concept that we have established for bipartite Qudits. And then talk a little bit about a very exciting quantum state estimation experiment called Quantum State Interferography. Okay. So now, starting with some fundamental quantum questions. Okay. Now, when we talk about quantum mechanics, and I know and I can see that there are lots of students here who are perhaps even from the MSc and even maybe advanced BSc level. So some of the things which strike you when you really start studying about quantum mechanics is that some of these things seems to be a little bit out of the ordinary, right? And of course, these are the non-classical features of quantum mechanics. And so the question is, what do they reveal about the nature of physical reality? Now, we are all, in a macroscopic world, let's say. So how to reconcile our everyday experience of the macroscopic world with the quote unquote, I would say, weird behavior that you might think that this microphysical world described by quantum mechanics has? And this is a valid question. We are all living in a certain scenario. Do these quantum mechanical principles which seem counterintuitive actually fit in to our everyday life? So what is the answer to this? To what extent is it possible to test quantum mechanics in the macro limit? Okay. And so this brings us to this very important concept called realism. Okay. So what is realism? The classical realist worldview states that a system is in a definite state for which all its observable properties have definite values, independent of measurement. Now, I am at RRI, and one of the things about RRI is its trees. So outside my window here, beautiful view that I have of beautiful trees. And the belief is that while I have just changed my, position and I'm looking at my computer screen, these trees will remain with their beauty and their greenery. So this is an example, of a system which has definite values independent of whether I'm looking at them or not, right? So this is what we are used to. So now, however, unlike a classical state, the specification of a quantum state does not in general give the values of dynamical variables possessed by a system, okay? Thus, in general, a dynamical variable is taken to have no definite measurement independent value. So very different from what we are used to. So the idea is that a quantum system, you can't talk about its properties before measurement. So measurement reveals the property. Okay, and so no definite measurement independent value. In other words, a measurement according to quantum mechanics in general does not reveal a pre-existent value of a dynamical variable. Okay, and so in fact, this brings us to this famous quote attributed to Einstein, where he said that, I like to think the moon is there even if I'm not looking at it. In fact, we would all like to think of that, right? Like the moon should be there even if we are not looking at it. And so he was actually very disturbed, by this phenomena, by this nature of quantum systems, that they don't have a definite value before measurement. Okay, and so this is what was the thought process even with Albert Einstein. Okay? This brings us to John Bell, who of course is one of the first people to actually propose something to solve this conundrum, so to speak. And his very nice paper, especially students should definitely read it, on Bertelsmann's socks and the nature of reality. So Bertelsmann was a colleague of John Bell, okay, and so they have worked together in, on many things. And so in this, John Bell says that the philosopher in the street who has not suffered a course in quantum mechanics is quite unimpressed by Einstein-Podolsky-Rosen correlations. Okay? He can point to many examples of similar correlations in everyday life. The case of Bertelsmann's socks is often cited. So what was interesting about John Bertelsmann was that Dr. Bertelsmann likes to wear two socks of different colors. Which color he will have on a given foot on a given day is quite unpredictable. Okay. So, but when you see, and this was a figure in his paper, when the first sock is pink, you can be already sure that the second sock will not be pink. Observation of the first and experience of Bertelsmann gives immediate information about the second. So there is no accounting for tastes. This is a fun side of John Bell. But apart from that, there is no mystery here. And is not the EPR business just the same? In fact, isn't that what we say, that, there are these pair of photons, they are correlated. And so, if I measure one, then I know of what is happening with the other. Isn't that something similar to what even happens with these pair of socks that my friend Bertelsmann tends to always wear in a mismatched manner? And this is Reinhold Bertelsmann showing his socks in Vienna in 2017. Okay. So, but then of course the answer to the question is no, it's not the same. Here we actually have this predetermined knowledge that, they are a mismatch. So if I know one, I will know that the other is not pink. That is great. But this is not as an act of measurement per se. So the correlations that we talk about, the EPR correlations, or the correlations which are shared by entangled particles, actually reveal themselves as an act of measurement. And so this is what makes it different from something as familiar to Bell as Bertelsmann's socks. Now, the best known set of experiments which examine this notion or question of realism are those which stem from the theoretical work of Einstein et al. And of Bell, and are known as the EPR-Bell experiments. So they refer to measurements made on a pair of systems which have interacted in the past, but are now separated to a distance such that, according to the postulates of special relativity, the outcome of a measurement as one system cannot be causally influenced by the choice of what to measure on the other. And so this is, schematic of such an experiment. So John Bell's famous inequality was derived from the setup illustrated here. So you have a pair of spin-half particles, and they're prepared in a state of zero angular momentum, and each propagates freely in opposite directions, right, to the measuring stations called Alice and Bob. That is the traditional name. So Alice measures the spin in a direction A, while Bob simultaneously measures in a direction B. So in a hidden variable theory, the measurement results are predetermined. So the hidden variables might decree, for example, that if Alice measures her spin up, Bob will measure his spin down. So this is what is the hidden variable theory, which is according to the, what we would believe if we were believers of local realism. Okay, and so this is what would happen if you believed in hidden variable theory. But of course, this is the schematic of, the EPR-Bell experiment. So essentially, we are again the same thing, but now with a little bit of more measurement details. So you have this source pair of photons, let's say, which are going in different directions. And so one of them goes to this measurement station A, the other goes to B. So if I, sort of expand on MA, there are two possibilities. So one is that, it goes through a beam splitter, and the other is gets reflected, let's say. So you have the plus and the minus. So in fact, between the stations A and B, you would have all these possibilities, plus, 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 minus, 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 plus. And that is how you construct, or of course not you construct, but the Bell inequality was constructed. So which is a sum and difference of these possibilities, of course, divided by the total number. And so these are these joint probabilities that we talk about. And this, if you followed, the local realism-based approach using hidden variable theories based on objective local theories, you will get this inequality to work out to be less than or equal to 2. Okay. So again, Bertelsmann says that when I derived that is I is Bertelsmann, when he derived Bell's inequality for the first time, he was really impressed that it was possible to discriminate between all hidden variable theories and quantum mechanics. How did John find his special combination of expectation values that contradicted quantum mechanics for certain sets of measurements? For me as a theorist, the job was done. Nevertheless, experiment had to decide which was right, hidden variable theory or quantum mechanics. So this is what sets the stage, and as Prashant already mentioned very nicely that, our job as experimentalists is of course to, give experimental credence to all these ideas which otherwise would remain just theoretical constructs, and then take it further to technological ramifications. And so Bell inequality is a perfect example of such a journey. Okay, and so this is again from Bertelsmann's paper. So regarding the classic experiments, and I think the students, for the students I included this, will be interested in the history of how this evolved. So the first to become interested in experimentally exploring Bell inequalities, and of course nowadays there are several, was John Clauser in the 1960s. Okay, at that time, working in the field was a courageous act. Clauser relates, for example, how he once had an appointment with Richard Feynman to discuss an experimental EPR configuration for testing the predictions of quantum mechanics. Feynman immediately threw him out of the office, saying, well, when you have found an error in quantum theory's experimental predictions, come back then, and we can discuss your problem with it. Okay, and so if this was the thing, then of course we would have nothing after that. But fortunately, Clauser remains stubborn, and that is what we sometimes need to do, be stubborn, and with Stuart Friedman, carried out the experiment in 1972. The outcome is well known. The results were in accord with quantum theory and in clear violation of a Bell inequality. Okay. Later experiments, notably by Edward Fry and Randall Thompson, confirmed the result. The 1980s saw a second generation of Bell experiments carried out, in particular by Alan Aspect and his group. Okay. Aspect and his colleagues worked with polarized photons, and their goal was to incorporate, and there are details. So a Bell inequality was significantly violated then. Again, experimental results agreed with quantum mechanics predictions. So in Bertelsmann's opinion, the Aspect work was a turning point. The physics community began to realize that such explorations were getting at something essential. It was not philosophy. It was real science, and it was actually more than that. It was actually also with experimental verification. Research started into what is nowadays called quantum information and quantum communication, a flourishing field. And this is a beautiful trajectory from fundamentals to experiments, testing the fundamentals, and then the realization of technology. And this is what was celebrated by, this very nice blog, on Bell's inequality 50 years later, which you'll find in Caltech. So what was special about this, is what Preskill writes. Okay, so this is the Jubilee year, and this was about entanglement and EPR and so on. So why is it such a big deal? Bell showed that a quantum system is more than just a probabilistic classical system, which eventually led to the realization that accurately predicting the behavior of highly entangled quantum systems is beyond the capacity of ordinary digital computers. Okay, and so he says 1964 was a good, Higgs and others described the Higgs mechanism. Okay, Gell-Mann and Zweig proposed the quark model, and Wilson and Penzias discovered the cosmic microwave background. And okay, so these developments all continue to reverberate 50 years later. And we are still looking for evidence of a new particle. And at that time, it wasn't yet done, the Higgs boson. But Bell's legacy is that quantum entanglement is becoming an increasingly pervasive theme of contemporary physics. Okay, quantum computers, awesome power, crucial feature of exotic phases of matter. And, so basically he says that all these frontiers of physics are advancing because of Bell's discovery. And so then he says that, all these great people have done great things in 1964. But there could be others who could have also done it, and he names them. But it's not obvious which contemporary of Bell, if any, would have discovered the inequality in Bell's absence. And that is why, it is so beautiful as something that has evolved, and it was celebrated. The 50th year was celebrated in Caltech and of course in other places. So having said that, now we come to Anthony Leggett, who raised a very fundamental question again. So we've talked about the Bell inequality, we've talked about its evolution, but now comes this point, the original point. Does nature differentiate between micro and macro? Okay, so of course Schrodinger's cat paper actually points this out, that there is no good reason to accept this division of the world into a microscopic regime where quantum mechanics reigns and a macroscopic one governed by classical physics, because quantum mechanics is a very totalitarian theory, and if it applies to individual electrons and atoms, it should prima facie equally apply to macroscopic objects made of them, right? And so this famous example of the Schrodinger cat, and it's a very valid question, of course. So which brings us to these two key notions, which describe the macroscopic world. So one of them is stemming from this local realism, local realist inequalities, which apply to bipartite or multipartite systems. And then, of course, there is this question of macro realism, which leads to macro realist inequalities, where you can actually test the quantumness of a single system. Because here in the Bell scenario, you usually would require two or more systems to be entangled with each other, which brings in obviously the concept of non-locality and so on. But what about a single system and its superposition? If you want to test that, you need something else, and that is where these inequalities come into being. So there are tools for testing or probing quantum reality. One of them will be the Bell's inequality and its variance. So these are testable algebraic consequence of the combination of the notions of realism and locality. Okay. And so these are incompatible with quantum mechanics. Then we have the Leggett Garg inequality and its variance, which are also testable algebraic consequence, but combinations of realism remains constant. But then we replace locality with what is called non-invasive measurability. Okay, and we'll discuss that as we go through the experiment. And again, this is also incompatible with quantum mechanics, and this is called macro realism. So the Leggett Garg inequality is a temporal analog of Bell's inequality. So in Bell's inequality, you have the non-locality, and so you have the non-local realism being violated. Here you have time-separated correlation functions corresponding to successive measurement outcomes for a system, whose state evolves in time. And so you're talking about correlations in time as opposed to correlations between 2 points in space. Okay, and so notion of realism is invoked in deriving LGI by assuming that a system during its time evolution is at any given time in a definite one of the macroscopically separated available states. And that is how you form the superposition. Right? So non-invasive measurability is assumed, which means that in principle, it is possible to determine which of the states the system is in without affecting the state itself or its subsequent dynamics. So you don't have an invasive measurement. So essentially, you can figure out which of the states the system is occupying without causing any invasiveness, and then or its system's subsequent dynamics. That is non-invasive, and it's a very difficult thing to achieve, of course, experimentally, right? So the original motivation for LGI was to use it for probing the possible limits of quantum mechanics, okay, in the mesoscopic macroscopic regime. Example, systems, experiments involving the RF squid device and so on. And so these are all various experiments that have happened towards this direction. But in recent years, the quantum mechanical violation of LGI and its implications have been extensively studied for various types of microsystems to probe their non-classicality, okay, ranging from solid-state qubits to nucleus spins to electrons to photons. And all this without involving the notion of locality, which is important. Which brings us to our experiment, which is a loophole-free interferometric test of macro realism using heralded single photons. So what are the key features of our experiment? This is the first loophole-free experiment wherein both the LGI and WLGI inequalities have been decisively violated. Okay? And it is a comprehensive refutation of the classical realist worldview, along with measurements ensured to be non-invasive. We have a perfect matching of these observed violations with quantum mechanical predictions, incorporating experimental non-idealities. And this sort of analysis has not been done in earlier experiments. So if you violate LGI, you are basically saying that, okay, you have violated macro realism. But to actually have it match beautifully with a certain theory, is something else. And that is what we have done, where we have matched it beautifully with quantum theory itself. Okay, and it gives us a powerful platform for harnessing this most general, unambiguous nature of the non-classicality of single photon states towards various information theoretic applications, where the single photon is a ubiquitous workhorse. Now, why is a loophole-free test important? Okay, so these are the various loophole-free tests which were done for the Bell inequality. 3 groups, in the same year, they reported these results from all across the globe. And these were the loophole-free Bell tests. And so you can see from the year 2015, it was almost 40 years since the first violation, from the Alan-Aspect experiments as well, when the loophole-free ones came along. So it takes a lot of effort and time to actually get a loophole-free experiment done. And so why is it an important achievement? And this is something which is summarized beautifully in this article that was written after those Bell experiments came about. Of course, it's great that, you are without any doubts, you're proving that quantum mechanics is real and complete, but, you're developing but they are also developing new capabilities in quantum information and security. So loophole-free Bell test demonstrates not only that particles can be entangled at all, but also that a particular source of entangled particles is working as intended and hasn't been tampered with. So now this sets the ball rolling, for perfectly secure quantum key distribution and unhackable sources of truly random numbers, which is what we are using violation of. So as Prashant said, now you hear about violation of Bell inequality a lot in this context, of QKD, randomness generation, and other applications. But then, of course, when it started, it was a fundamental idea. Similarly, we see that, our loophole-free experiment, and thankfully there are no other groups which have claimed that, as well, is going to set the stage for all these beautiful applications that LGI will find itself in as well. Okay, so we have, of course, as I said, violated both the LGI and WLGI in our experiment. And so this is the Leggett Garg inequality expression. So where you have these joint probabilities measured between times T1 and T2, T2 and T3, and T1 and T3. So it's 3-time measurements. Okay, so joint probabilities between different possibilities. And so from the macro realist scenario, you will get this to be bounded to be less than equal to 1. The quantum mechanical bound is in fact 1.5. For WLGI, it is a subset of the probabilities that go into LGI, where it is bounded to 0, where the quantum mechanical bound is 0.5. Okay, so LGI and WLGI are both necessary, but not sufficient conditions of macro realism. Okay, so simultaneous violation provides a more robust violation of the notion of MR. And of course, the WLGI expression involves a significantly lower number of measurable joint probabilities. So that is very nice because, it is a more experimentally friendly parameter that way, because it's prone to less error and hence a better match with quantum mechanical predictions. And so these are, so this is the system, it is undergoing a unitary evolution. And so you're measuring at different points of time between different possibilities. And that is how you're constructing the inequalities. Okay. And so this was the proposal that we had in the paper, where, which had 2 concatenated Mach-Zehnder interferometers. And here we are, defining the macroscopicity by the separation between the 2 arms of our Mach-Zehnder interferometer. So here you have a single photon. If it goes in the upper path, we call it -1. If it is in the lower path, it is +1, and so on. And so the separation divided by, the wavelength of the photon gives me the macroscopicity, which is as high as 10 to the 4. And so this is very important, that the macroscopicity parameter need not necessarily always imply mass, which is a misconception. So just increasing masses is not the way to get to macroscopicity. It is a context-dependent definition, and many different experiments have been done with different contexts and different macroscopicities defined. And in this experiment, we have closed all these 5 known loopholes for the first time. Okay. So going on to some of these loopholes, the first is the clumsiness loophole, and it is as good as it says that, you are trying to do a measurement. It's very difficult to do this without causing some invasiveness. And that is what brings about the clumsiness of your scenario. And so what is a standard way of, dealing with this clumsiness loophole is what is called a negative result measurement, where the measurement in which outcome is inferred when the detector is not triggered. Okay, and so this is the idea. So if you want to measure, let's say P, T2, T3 plus plus, so you have plus plus, so the detector is here in the minus arm. So all those events which didn't contribute to this contribute to the plus plus scenario. And so obviously if you don't detect, then the probability of being clumsy is low. And that is the basis for negative result measurements. But measurements are inherently invasive. So non-idealness of the negative result measurements can result in classical disturbance that can lead to a false violation, okay? And so this is the clumsiness loophole. And so what do? So we went on to do something more. Other than negative result measurements, we also went on to do what is called satisfy the two-time no signaling in time conditions. And this, I don't want to get into the detail of it, but essentially the operational or statistical form of NIM is equivalent to the no signaling in time condition, which tells you that the choice of measurement at any instant does not affect the statistical results of any measurement at a later instant. So no signaling in time, literally. And so this is something we actually satisfied for all the corresponding two-time NSIT conditions. Okay, so this together it forms the LGI. So there are 3 experimental runs. So each of them we have satisfied its corresponding no signaling in time to give an even stronger non-invasive measurability for our experiment. Okay. Then we come to this very well-known loophole, which is called the fair sampling loophole or the detection efficiency loophole. Now, this is the assumption that all detection efficiencies are 100%. In reality, this is not the case. You will never get a detector which has 100% efficiency. So what we have done, we have calculated the minimum detection efficiency that is required for our experiment to be loophole, detection efficiency loophole free. And for LGI, it comes to 85%, and WLGI, it came to 78%. These are very large numbers and very difficult to satisfy using the normal detectors that we use in the lab. Okay. So then we went on to something else. We went on to a modification in the measurement strategy. So you, instead of using detectors in the intermediate parts, intermediate times rather, we used perfect blockers for negative result measurements, and we shifted all detection to the end time, which is T3. And of course, there is the non-invasive measurability assumption, and using arrow of time, which is that time goes forward, always forward equations. This is of course your Leggett Garg, but so we were able to come up with modified, expression, and that's a very long calculation, and so I won't get into that. But the idea is the detection efficiency eta just comes as a factor in the denominator in the end. When we do all these things, replace it with a perfect blocker, push all detection in the end, then any non-zero detection efficiency will give us, will circumvent the detection efficiency loophole for us. And so this was one of the USPs of this experiment about our way of how we could, circumvent the detection efficiency loophole. Okay? It doesn't even exist. It's irrelevant in this context. Then there is the multi-photon emission loophole. I won't get into the details because it wasn't very important in the end. The fact that we are dealing with a single photon is again an assumption. You can have more than one photon in an experiment, and so we actually did sub-experiments. This experiment involved several sub-experiments. This was one of them, where we figured out what is the fraction of the total set of runs that corresponds to the occurrence of 2 photons within our experimental setup. And this came out to be 0.0023. And so if you use this parameter, the LGI bound is changed from 1 to 1.0046 and WLGI from 0 to 0.0012. So it was only in the 3rd decimal place. And so in fact, it wasn't essentially a very important consideration for us. The change bound was very small. Okay. So this was our actual schematic where we actually replaced the concatenated Mach-Zehnder with, one of them with a displaced Sagnac interferometer for its inherent phase stability. And of course, several experiments have happened on closing the clumsiness loophole. These are all earlier experiments, but the other loopholes have not garnered much attention till ours, where, especially the detection efficiency loophole, which has played a critical role in many Bell violation experiments, have not been analyzed in earlier LGI experiments. Okay, and so this was our result. And as you can see, this is your macro-realist bound. This is the quantum mechanical bound, including experimental non-idealities. And this was our experimentally measured value. And you can see that the experiment matches perfectly with the quantum mechanical predicted range within the uncertainties. And so, and this is the extent to which we constrain non-invasive measurability. So so this was a beautiful result at the end of almost 3 to 4 years of doing this experiment. And in fact, this is during when Tony Leggett actually visited RRI. While we were doing this experiment. So some of the discussions with him have also been very helpful, gaining perspectives on this topic. Okay, so right, so this is where I wanted to take a pause and say that this was the first thing I wanted to talk about in somewhat detail, which is this first loophole-free violation of the Leggett Garg inequalities using heralded photons. Next, I move on to another topic which is of great interest to me and my lab, which is higher dimensional quantum information. Okay, and so why do we need higher dimensions? And so essentially the idea can be summarized in a nutshell that, one of the things which we have been addressing as a community is trying to increase the number of qubits which are in superposition, right? So 2 to the power 50 is a number which had been a holy grail for some time for the computing perspective. So 50 qubits will give you the first, quantum supremacy or whatever they want to call it. But then using higher dimensions, I can actually drop that exponent. So instead of 50, if I use 3 state systems, the 50 drops 33. Okay, and similarly, if I keep increasing the dimension of the system, I will deal with less number of systems. So I can use Qudits to decrease the size of the system while maintaining the same Hilbert space, same access to the state space. Okay, and so this is basically a motivation for studying higher dimensions. And so what we have done in our lab is come up with a new way of generating spatially correlated Qtrits and Qdates using spontaneous parametric down conversion. So as I said, a Qtrit is something which has 3 basis states. Okay, and one way in which you can do this using photons is by having a photon incident on a plate, let's say with 3 apertures or multiple apertures. And so you don't know a priori which one it goes through. And so you are able to actually generate a superposition that way, where 0, 1, and 2 refer to the spatial degree of freedom of the photon. Okay? So this is one way, and there has been a lot of work, including my own while I was a postdoc still at IQC, which have dealt with this way of using spatial Qudits. Okay, but what we went on to do is do this in a different way in our lab, which is what we call the pump beam modulation technique of generating Qudits. So instead of placing apertures in the path of the down conversion photon, what we went on to do is place them in the path of the pump beam itself, as a result of which the pump beam takes on the properties of this particular structure that is imposed on it, and then the resultant photons already carry this pump characteristic through. Okay, and so this is the experimental, how it looks in the lab. But then, this is the idea: transfer of the profile of the pump to daughter photons. So usually we are used to transferring a Gaussian profile because that is the standard pump that we are used to. But here we have done, this sort of a profile at the pump, which has been carried through to the detector. So the spatial structure of the pump is carried through faithfully to the resultant single photons, which are called the signal and idler. And we saw very nice 1, 1, 2, 2, 3, 3 correlations between these pairs of photons with a very high correlation coefficient of 0.9, which is great for experiments. Okay. And so, but then at this stage, we do not know a priori whether these photons are correlated in the classical degree, classically or quantumly. We know, we have a hint that this is quantum because we also tried to do this experiment using the pump itself without using the down conversion photons, and we don't get these correlations, which means it has something to do with these single particles of light. But there is something more one needs to do to prove definitively that you have quantum correlations, and one of them would be to try and find a signature for entanglement in these systems. Okay, and so this is something we have done very recently, where we have actually come up with a beautiful way, I would say, of actually quantifying the amount of entanglement in these bipartite Qudit scenarios, avoiding the conventional tomography approach. So usually what you would do is you would do quantum state tomography, and from that you will be able to extract some measure of entanglement. Okay? But quantum state tomography scales very badly with dimensions. So it's actually scales as d squared. So you do not want to use quantum state tomography for beyond a certain dimension, because it just gets very unwieldy. So what we have done is an alternative approach which we have devised, wherein we have derived a monotonicity relation between negativity, which is a measure of entanglement, and the sum of Pearson correlation coefficients for arbitrary dimension. Now, what is Pearson correlation coefficient? It is actually a statistical correlation measure. So essentially, we have derived a monotonicity relation between a measure of entanglement on the one hand and statistical correlation measures on the other, which means that by measuring the statistical correlation measures, we are able to tell you exactly how entangled the system is. It is not about entanglement witness, okay, which is a common thing to do to come up with whether you are entangled or not. It is not just certifying entanglement, it's actually quantifying it and telling you how entangled, which is important for applications where you need to know exactly what you're dealing with in the system, because nothing is perfect really in experiments, right? So we have derived this relation between negativity and some of mutual predictabilities as well. So essentially, these are all different classical correlation or statistical correlation measures, and a monotonicity relation between entanglement of formation and mutual information. Okay, and then we have done the experiment, which is the first direct measurement of an entanglement monotone, and we have shown that negativity and entanglement of formation are non-equivalent entanglement measures. For people who are working in this domain, you will realize that this is very interesting, because in the qubit scenario, for the pure state case, we usually don't have a preference of one measure over another. If we measure concurrence, we would say, okay, if we measure negativity also, it's not going to give me a different amount of entanglement. But we have found that negativity and entanglement formation are not equivalent entanglement measures for higher D. And this is this first experimental demonstration also of this non-equivalence. And so these are the papers which I would encourage you to look at, which have a lot of detail about what I've just said. So this is the theory work where we have actually shown this for the 2 Qudit mixed states. Okay. And of course, importantly, this uses only one set of complementary measurements, right? As opposed to the number of measurements that you will need for the D-square scaling. And here, this is the experiment where we have done the experiment as well as the theory for the pure state case. Okay, so together they form the entire package of theory as well as experiment in this domain. And so these are actually the results that we have derived, which again, I don't want to get into the details, but this is your negativity and this is the mutual predictability and so on. And this is the schematic of the experiment. And so, this is, your interference. So where, observing interference is actually taken to be a certification of entanglement, but we have gone beyond that and also quantified the same. And we're working on different approaches towards linear optics quantum information and, various QIP protocols and higher dimensional gates is in our agenda over the next few years from the lab. And so this is a snapshot of some of the work that we have done in this. And this is the article that Prashant referred to, which you can have a look at, especially students, where I have given a popular level summary I was invited to give on this, whole exploration of higher dimensions. Okay. Carrying on with the theme of higher dimensions, I would like to end this talk over the next few minutes, describing yet another experiment that we have done in higher dimensions, with an advantage in higher dimensions, which is now for a different problem. So far, what we have discussed is about a new architecture where we have generated bipartite qubits in the lab and come up with a new way of quantifying their entanglement, right? Both in theory and experiment. But one of the other interesting problems, of course, in quantum information is estimating the quantum state. Okay, and so we have attacked the problem in a very different way, using interference again as our tool. It happens to be the tool in many things we do. Even the Leggett Garg experiment was based on interference. We have used interference as a certification of entanglement in the next set of things I told you. And here again, we are using interference for a whole new application. Okay. And so this is the primary paper on this, where we have come up with a new scheme to estimate the quantum state, which is called Quantum State Interferography, along with my collaborator at HRI, Urbasi. Okay, and these are other papers which actually are also very relevant. So if anybody is interested in studying this piece of work, you will have to actually also study these, because these lay the foundations for this experiment. Okay, so there are various things both in theory here and in experiment that we have already shown, which form essential ingredients to understand this experiment. Okay, why estimate the quantum state? A question that you may have. Now, why not? I mean, the wave function is actually used to completely describe a quantum system and is central to quantum theory, right? So in theoretical calculations, one can assume a form of the wave function and proceed with the calculations, which is what we tend to do. But what about experiments? For example, quantum computing. Precision and knowledge of the state of the system leads to precision in all that follows. Okay, we simply cannot assume something and think that our assumption is right. something we can do in theory, but not in experiments, because that will have ramifications in a domino effect for everything that follows. Okay? So once we, and of course, even from a theoretical perspective, once we know the density matrix, we can calculate many important quantities. For instance, reduced density matrix can be used for calculating entanglement entropy, as many of us tend to do. So in our work, we use one of the most fundamental phenomena in quantum systems, that is interference, to devise and experimentally demonstrate a new method for quantum state estimation, which is called quantum state interferography. And it is basically this is our central question: can we have a device which, without any change of internal settings by the user, we can determine the quantum state of the system? And so this is what we are trying to answer here. Okay. So before that, I would like to say that, this is not a new problem. Estimating the quantum state has been a problem, and people have been approaching it through different perspectives for decades, right? So if we walk through some methods, the most common method is, of course, quantum state tomography. And this is similar to the CT scan that we are all familiar with. If you want to do a CT scan of the brain, what is it that you do? You actually take different projections of the brain, images of different projections, and you stitch it together to form the image of the brain, because you don't want to have an invasive measurement there. And so the T is common. So the tomography is what is done in CT scan. Similarly, even in quantum scenario, we do quantum state tomography, where we take different projections of the quantum state, measure them, and then reconstruct the quantum state. Okay, so this is what is a standard way of doing things. However, having said that, basically, quantum state tomography has a very bad scaling with dimension. As I said, it scales as d square. So there are lots of things people have tried to reduce these number of measurements. For instance, this is a paper in which they show that 5d minus 7 observables suffice to uniquely determine any pure state. Okay, and so this is the QST. Okay, and so best scaling for pure states 5ip minus 7, mixed state remains d square minus 1. Then there are all these various experiments where they have tried to do direct measurement of the quantum wave function. The London one is a very well known one. And then this was done for a different degree of freedom. This was polarization. That was London did a different approach. This essentially brings us to this direct weak measurement. Okay, so I won't get into the details of weak measurement because of lack of time, but this is what we call the weak value. And so if you are able to, so you can actually expand a quantum state in terms of this. Okay, so the weak value of the pi 0 and pi 1, where these are the projection operators, and then you can define this weak value this way. So essentially, you can say that by determining the weak value, you can have a way of determining the quantum state. But then, as you can see, this psi actually appears in both the numerator and denominator. So this is one example, and then many experiments. This was an experiment on OAM degree of freedom. Then Lorenzo and collaborators came up with this very nice, paper where they compared between different direct state measurement and tomography, because all these were attempts at direct state measurement, right? So they did this comparison, and they find that direct state measurement is much less precise than tomography. Okay, but it is surprisingly robust to its inherent bias, which introduces an unavoidable error in the reconstruction. Okay, so this is something that they found. So then, of course, instead of weak measurements, people tried to do strong measurements to give a better direct measurement of the wave function. And so these are all these strong measurement results. Okay, so this brings us to quantum state interferography, which essentially involves no weak measurement. It is not a direct state measurement. It is essentially a new single shot state estimation method using interference as a tool. Okay, so here in these cases, the idea was to reduce the number of measurements and get the wave function. In our case, so here they have less post-processing, but in our case, we have reduced the number to in fact 1, and we have more post-processing, which is great because, the more the number of measurements, more the error. So we would say we have an advantage over these techniques where the number of measurements is, not less. It is basically they have less post-processing. So this is a contrast to these direct state measurement techniques. Okay, and so this is how it would scale with dimension. So as the dimension of the system is scaling here, without any assumption QST, it will require these many measurements. Okay, and so for quantum state interferography, as you can see, for pure state assumption, we would require this. number of measurements. So we have been able to show this technique for pure states. So that's why I'm sticking to the pure state comparison. So this is QST assuming pure states. This is QSI assuming pure state. And as you can see, we have a very nice advantage over that. This is the schematic of the experiment in the lab. However, having said that, what you would need to do in order to do QSI is essentially understand this slide. So this is how you would represent a density matrix. Now, if you evaluate two expectation values, which is of the pi0, which is essentially the projection operator, and the sigma minus for an unknown state, you can see that expectation of value of pi0 gives you the A, and the expectation value of sigma minus gives you the B to the I theta. So by doing these two, you can in fact determine the quantum state. But one catch here. In order to do this, you have to do this. And this is the spin ladder operator. And as you can very well see, this is a non-Hermitian operator. So how will you determine the expectation value of a non-Hermitian operator becomes a question. And in order to answer that question, this paper comes in handy, where we have shown that you can measure non-Hermitian operators via weak values. And so the essential math here, and of course there's a lot of detail which I cannot get into, but this is what you need to understand. So if you have this non-Hermitian operator, you can use the polar decomposition theorem to decompose it into a product of a Hermitian and a unitary. Okay, so this is your unitary, which is the sigma x, right? And this is your Hermitian. And so essentially now, if you see, for people who are familiar with optics, you can see that this basically boils down to a half-wave plate at 45 degrees. And this boils down to the linear polarizer at 0. And so by using these optical elements now, you can get a feel that you can measure the expectation value of a non-Hermitian operator. But one catch is that in this way of doing it from weak values, the wave function still remains in the denominator. So for state determination, you have to know phi psi as well. And that is a circular problem. You can't know psi to determine psi. So in order to solve that problem, we came up with a way in which we can measure the average value of a non-Hermitian operator in an interferometric setup, where we can do this without this circular argument. Okay? And this is how the interferometric setup looks. You essentially have the same ingredients here, but now you have this calculation, which is a detailed one, which I won't get into. But if you measure the intensity as a function of phase difference, you'll be able to represent it in terms of this expectation value of pi0 and this sigma minus. So by measuring the intensity pattern, I can actually derive these two quantities, which are required, as we have discussed, for estimating the quantum state. So you don't have to get into measuring the weak value. And in fact, we went on to show, this is what you would get if you did this using weak value. Okay. And this is, you have the amplification and so on. And this is, in these regions, as you can see, the weak value blows up. But this one doesn't have that problem. So in fact, it's better because you don't have this amplification region causing issues when we do this interferometric technique. And so all this comes together in QSI, where we take in these ingredients of measuring these expectation values using an interferometer, and the fact that you can have an interference pattern and infer things from it. And we bring all this together to reconstruct the quantum state. Okay. And so then this is how a pure state would be represented. This is the mixed state. So in order to do that, again, I'll skip this one. This is the important slide for students to remember, that if you measure an interference pattern, you can represent it in this form where you have these quantities, theta, mu, and phi. And by measuring these three parameters from your intensity distribution pattern, that is the phase shift, the average intensity, and the visibility, you can actually infer these three quantities, which in turn helps you infer the quantum state. Okay, so this is the nutshell. And these are the details, which I will skip for now. And this are the results. So you can see we have very nice results. In terms of pure state reconstruction, we have very high fidelity of averaging to 98%. For mixed state, also it's 95, 96%. And it's exceptionally good and very comparable to quantum state tomography. And this is another thing that, an idea that by using this, we can now think of a miniaturized device version, which is like a pocket-sized version of a quantum state estimator, which also we have proposed. By using these sort of elements, we can have a small micron size device for quantum state interferography. Okay. And this is the Qudit extension, and all the math is there in the paper for you to see. But the important ingredient is that you can now measure the quantum state using only d minus 1 measurements instead of d square minus 1. And for, of course, for, as you can see, for 2 dimensions, it becomes a single measurement. You can also use a trick where you can have a horizontal and vertical interference together, and by measuring all of them in the same plane, you can bring it down to again 1 measurement. But that's something which requires a little more discussion. And we can also infer the entanglement of a bipartite system by using QSI with less number of measurements again than QST. So it can be used to determine an unknown qubit state using a single shot measurement. If a bipartite state of qubits is known, it can be used to quantify the entanglement within a single setup, and it has a fantastic scaling advantage over quantum state tomography. So using interference as a resource, fundamental phenomena of interference, they've come up with a state estimation technique, which we are now looking forward to, in fact, miniaturizing and commercializing as we speak. Okay. So with that, I think I'm right on time. So I would like to thank you for your attention. And we have just celebrated 10 years of our lab. And so these are some pictures from there. So with that, yeah, thank you for your attention.
Yeah, thank you, Mr. Sinha, for a very, very nice talk. And because, good for me, I could get some nice references and some recent experiments. And there are lots of questions. Maybe some of you can open and ask. Yeah, for example,
I can see some questions.
Yeah.
Quantum key. QKD stands for quantum key distribution. That's correct. Then why one negative sign appear in the mathematical? Yeah, this is something which we cannot. It needs a board to actually be able to show this. So you can look up the derivation. If you have questions, you please get back to me, because this is a question which I just can't answer in words. Cause, if the answer were one, always yes, that is true. So if you have worked it out, then very good. You will see that you will be able to show this. So of course I didn't talk about the 2√2 part of it. So the 2 and less than 2 is the classical part, but anything greater than 2 signifies quantum. And of course, if you input these values, you will be able to get the 2 very nicely. And so that is in fact towards the right answer. So what full form for LGI, Leggett Garg Inequality? I hope that was clear when I gave the rest of the talk. PDF will be available, I don't know. Prashant, some of the questions.
Excuse me. Hello.
Yeah. Yes, please.
I have a question.
Yes,
regarding this non-Hermitian matrices that you're measuring. Are they PT symmetric?
Yeah, so we actually do not, concern ourselves with, that is a very interesting question. So whether, these are PT symmetric or not, our concern is actually to be able to come up with a scenario where we can take a non-Hermitian operator, which is actually a very famous one, the spin ladder operator, and be able to show whether this decomposition theorem is actually realizable in the lab. So our approach is kind of, complementary to the entire history of PT symmetric quantum mechanics, where we are able to use Hermitian operators and unitary operators to reconstruct the non-Hermitian operator. So that is what I would, say in a nutshell to that. I don't know who asked it, but thanks for the question. I think Shaurin has raised hand. Prashant, I'm getting lost as to whether I should read the questions or.
Shaurin, are you able to?
No. Okay, Urbasi. Yes.
Hi,
can you hear me?
Yes.
Hi.
Very well, thank you.
Hi, Urbasi.
Hi.
Thanks for the nice talk.
Thanks.
Actually, we are inside an interview board. Both me and Prashant, we are kind of shuffling back and forth.
Okay, great.
Okay. So the question
you
is.
should ask them this question. What is LGI? Yeah. Okay. Go on. Yeah, please.
So one thing which bothers me, of course, there's a non-Hermitian aspect which I'm very much interested in, which I want to ask next. But before going there, one thing which bothers me with this LGI is that when you're looking at LGI, is it that we are checking the wave mechanics part of quantum mechanics, because H-cut never appears anywhere in the inequality. That's something which bothers me. In a sense, when I say it's quantum, I say it from the that if I have wave mechanics, I will actually probably violate all these things. For example, even classical light, probably with the polarization degree of freedom, will give you very similar results. That's one concern. The other concern is when you are thinking of Bell's inequality, it's really multi-party. There is a multi-particle aspect of it. which when you say temporal correlation, it's the same guy being measured twice. So it really doesn't have this intrinsic multi-party character, which is very important for entanglement in a sense. You can say entanglement in time, but it doesn't really carry the same sense. So these are the two things which are missing. And do you have any idea how we can put them back? I have been thinking of.
So I'll answer the second question first. So,
sure.
You do not, so this was, I sort of said that in one of my slides, the idea being that, what we are, so there are two aspects to this, right? One of them is superposition and the other is entanglement. So now in the Bell inequality scenarios, what we are checking, of course, we are actually concerned with whether realism holds or not. That is our primary focus in all these different genre of experiments. So for the Bell violation experiments, we are actually testing this using entangled particles because, of course, they give us this natural way in which we can test, a local realism and violate it, so to speak. So if we violate it, then we know if it is non-local, then the one thing remaining becomes realism. That is how it goes. That is the Bell part. But in Leggett Garg, what we are doing is we are actually testing whether, the superposition holds, the idea of superposition holds in macroscopic systems, right? So then, of course, we don't need this is not an experiment which is using entanglement as a resource for testing realism. What we are using as a resource is another very fundamental phenomena, which is superposition, right? So the single particle can actually be in a superposition of macroscopically distinct states. And I think I mentioned that this macroscopic distinctness need not always manifest itself in terms of, massive particle and so on. You can define macroscopicity according to the context. For instance, the famous experiment is using this Qudit, right? Where you have this current going in a clockwise and anti-clockwise, and the difference is taken to be the macroscopicity parameter. So Leggett Garg is based on a completely different principle, which is being used to test realism. So both are parallel.
I agree with you.
Yeah, and so entanglement is time as a concept.
But Urbasi, can I say one thing? In a sense, when you are looking at macroscopic scale quantum mechanics, it definitely intrinsically involves heavy amount of entanglement. For example, superconductivity. The fact that there is a superconducting state is, of course, telling you that the fermions are badly entangled inside, and that's what gave rise to this giant wave function of macroscopic number of particle which is behaving quantum mechanically.
No. But again,
so I think, of course,
I want to interject here because, again, there is this confusion about macroscopicity actually meaning big. So, so the whole idea of macroscopicity need not be big in the sense of, a big size or a big mass.
Avogadro number, you mean?
Yeah. So it is not always in that genre. So, for instance, all the recent experiments that have happened in LGI, which are not with trying to scale up the mass, that is another field which people are very interested in. But the other way is, LGI actually gives you, a stronger realization that you are in fact dealing with something which is inherently non-classical. So of course, the idea being that you are violating, so non-classical is what we are talking about, and we need not be talking about it.
Yes.
And so your first question was about the quantumness of LGI.
I agree with.
The quantumness of LGI was your first question. So of course, the LGI inequality was derived using, of course, assumptions of non-invasive measurability and realism. So it is, the inequality violation is what we are talking about, right? So the inequality has in it assumptions which in fact are specifically not quantum, right? So they are, of course, based on assumptions of realism and non-invasive measurability. And together you can, the math is very nice because it's very analogous to Bell derivation. You can show that, this inequality comes about. And
yes, I agree.
But now by violating this, what we are saying is that we are violating macroscopic realism. But the fact that our particular experiment actually matches one such theory, which could be, a contender for something which satisfies this violation is quantum mechanics. So, there could be, for instance, the Bohm model and things like that, which are also, possible contenders for such a violation. But we have shown the match with quantum mechanics. So, you don't need quantum mechanics to derive LGI. So the entire argument does not hold what you kind of, asked in the first question. If you see what I mean.
All I was trying to say is that even wave, I think I agree with, in a sense that the wave mechanics will also give you such.
Of course, you don't. LGI depends on interference. So our experiment, as you have seen, intrinsically depends on what happens when there is interference of a single particle which is going forward in time. So single particle is a crucial ingredient, and as I showed you the gamma parameter, that our doubleness is in the 3rd decimal place. So the fact that there is a single particle showing interference tells you that we are testing both the particle and wave nature of our system.
Sure, agree.
So we will take just one more question, Pranav. You have been raising hand for quite some time. And many of you who are interested, please send an email to Professor Sinha.
I'll be very happy.
Pranav, you can ask the last question.
Yeah, thank you, ma'am, for this amazing talk.
Thank you.
So I wanted to ask a question about qubits and qubits. So I have seen that there are already a lot of algorithms about qubits. But as you said, if we use qubits or qubits, the number of required bits would be much less. But wouldn't it also require a lot of new algorithms?
Yes, and that's a great question. If you're a student, then I don't know whether you're a student or not. But then if you are, then this is indeed why I find something that I missed, because the 50-minute was, I have a stopwatch here, so I was trying to do the 50-minute very diligently. But one thing that I really like to say here is that why this is interesting. Of course, it has the advantage from the computing perspective in terms of the number of systems being less. That's a practical advantage, and we are all very happy for it. In quantum key distribution, there are theory papers by very famous groups which tell you that you have higher key rate and lower error rate and so on. So great things to study experimentally. But one of the other things which is also very interesting is that there is a need for coming up with a universal set of gates for the system in hand, coming up with the counterpart algorithms for the system in hand. So there is a lot of open problems in theory. And so that is why, this is a very fertile area where, a lot could be done. And in fact, the question you raised is one such problem, which of course we are already looking at separately, which I can discuss with you offline, but then, and many others. So something interests you and excites you if you have something to do, something that is left to do. Otherwise, if you just keep repeating things, it's not very interesting beyond the point. So this is why also this is an interesting field. And your question, of course, fits that very well.
Yeah, for example, I was already working on quantum RAM, and I found that the qubits have used in that. But also, on the other hand, there are algorithms that only use qubits. So I was much confused that we have qubits available, then why shouldn't we use them?
Yes, qubits available is an interesting point. It's very difficult to maintain qubits, because the whole idea is that it's a superposition of more basis states. So while it is great to explore, it is also difficult to maintain this coherent superposition. Okay, and so that is why we don't have that many systems where we have the opportunity to say that, okay, I trust the system, it's robust and it will scale and so on. So addressability is also a concern. So it is difficult to actually have qubits, but once you have them, there are lots of things one can do, is how I would phrase this. Yeah, thank you very much. And thanks, Prashant.
Yeah, I am really truly enjoyed your talk. Very, very nice. Very nice. Thank you very much.